In this module, we'll cover a brief overview on the injection molding process. In this module, we'll review the injection molding process as well as the flow behavior of thermoplastics in injection molds. Why do we need to do this? Understanding injection molding and the flow behavior is absolutely critical in order to properly use Autodesk Simulation Mold Flow software. In this slide, we're showing you an illustration of a typical injection molding machine. We have a hydraulic unit. There are some electric units on the market today as well. We have hopper, which holds our material. That's where we're loading it. The barrel, which contains a screw for feeding the material into the mold. And then the nozzle, which is naturally where the material is going to come out of the barrel and into the mold. To the left, we have our mold, which is forming our part. Now I'll discuss some of the injection molding terminology for a typical molded component. We have our sprue, our coal slug well, our primary runner system, our secondary runner system, the gates, and of course the part cavity. We have a polymer entrance point that will start at the top of the sprue, and that's where flow begins and fills through our sprue, through the primary runner, through the secondary, through the gate, and finally into the part cavity. Now we'll take a quick look at the injection molding process. This process is typically made up of several phases, the first one being filling. In the filling process, the mold's going to close. The screw is going to move forward to inject our polymer into our mold cavity, and we're going to start forming a thin skin on the mold wall. Packing. Cavity is basically going to finish filling under pressure control, and we're going to hold a pressure on that polymer as the part cools and the gate freezes off. After packing phase, we move into the cooling phase. And this is where the part simply continues to cool until it's rigid enough to withstand being ejected from the mold. During this time, the screw is also typically moving back and plasticating or building up your next shot just to save your cycle time. After we're finished cooling, the mold will open and of course the part will be ejected. The injection molding cycle is typically pretty linear. As we are discussing each of the four phases, you could see that we start in a fill time. After fill is complete, we move in the pack, then we move in the cool, then we move into the mold open time where the part's ejected. So these four phases, you add them up and that will give you your cycle time. As you can see, the pack and cooling times are typically a significant portion of your cycle, so this is where you can commonly leverage the software to optimize your cycle time. Now we'll take a look at the typical injection mold. In a typical injection mold, we have a stationary half and a moving half. So the stationary half remains in place, and the moving half is the one that will open up. The machine will open up and allow you to eject your part. Some may call it a core and cavity half, some may call it an A and B side. There are many different terminologies used, but this is just one. Of course, this is for a standard, very simple injection mold. There are other technologies out there where we may have some more advanced definitions and topics that we could discuss. I'll talk a little bit about injection pressure. So of course, the pressure is required to push the plastic into the mold cavity. This is what we're going to call our injection pressure. This is usually limited by your machine's capabilities. So you have a hydraulic pump or an electric motor on this machine that can only has a certain horsepower to it. So usually we're looking around 140 to 180 megapascals or 20 to 26,000 psi. Some modern machines can go as high as 300 megapascals or almost 44,000 psi. This can have a big influence on your final part dimensions and will ultimately let you know if you can produce this part in your machine, so it is important to be aware of this. There are many variables affecting injection pressure: part design, mold design, processing conditions, and material selection. Each area can be affected by other areas, so if we change our part design, that may mean that we need to also alter our processing conditions a little bit. So it can be complex getting into this, but that's what the software can hopefully help you with. It's also good to note that some are easily changed while others are not. You may be able to adjust your processing conditions, but you may have already ordered your material and have that in the warehouse, so maybe you are not allowed to change that. Pressure drives flow. Flow is driven by pressure, so it overcomes the melt's resistance to flow essentially. You can see that plastics flow from high to low pressure areas, and pressure will decrease along the flow length. So you can see our pressure in this graph is essentially 0 at the flow front and maximum at our injection location at the top of the sprue. Our part design will affect injection pressure as well. So part thickness, you can see on the left, we have a thin part at the top that's going to have a higher pressure. The thicker part we can assume will have a lower pressure. Surface area can also play an impact on our injection pressure. So more surface area, typically the part will cool faster, which means our pressures will be higher. Less surface area, the part will likely cool a little slower and allow us to fill the part at a higher temperature, lowering our pressures. So how does the mold design affect our injection pressures? So gate size is one. You can see on the top left there, we have a restrictive gate, which we can assume will give us a much higher pressure than the more generously sized gate in the lower left-hand corner. Flow length, or what would be dictated by your gate location, can also impact this. So a longer flow length, we can assume will have a higher pressure, whereas shorter flow lengths, in the bottom right image, you can see we're centrally gated there, will have lower pressures. So here's a good example how processing conditions can affect your injection pressure. So we did a quick study on injection pressure versus time, and here you can see how our injection time, as we start on the right side around 20 seconds, the pressures are very high, fairly high. So as we inject faster and faster, we're shearing that material, decreasing the viscosity, until we get to a point where we're starting to fill it so fast that we're not leveraging that any longer. So we want to make sure to keep our cycles to a minimum, so we're going to typically stay somewhere on the left side of that chart there in the green zone, without of course exceeding the shear stresses and shear rates for our material. Just to see how some other processing conditions can affect our injection pressures, melt and mold temps. So as we mentioned, temperatures can impact the viscosity of our material. So with the melt temperature, when it's higher, we typically have a lower pressure. If it's cooler, then we'll have a higher pressure. That's same can be said for the mold temperature as well. So cooler molds typically will need a higher pressure to fill because you're forming that frozen layer a lot quicker. And then hotter mold temperatures, they typically have a lower pressure. So how materials affect your injection pressure? Well, different grades of material can have different viscosities, which of course directly impact how much pressure we need to fill our part. So even when we're looking at something like a simple polypropylene, we can't make that assumption that all polypropylenes have a very similar viscosity or they're all the same. That's not the case. And as you can see in this graph, we have a high viscosity polypropylene and a low viscosity polypropylene. And you can see how over a range of injection times how that can change our injection pressures necessary to fill our part. In the previous slide, we took a look at how two different grades of polypropylene can differ drastically from one another. So it only stands to reason that we can also see the same between different families of materials. So in the graph below, you'll see a polycarbonate versus an ABS versus a polypropylene. You can see that polycarbonate is quite a bit different from the ABS and polypropylene, so we need to be aware of this in our material selection. And one way we can help us and guide us in looking at different grades and between different materials is maybe by using that MFR number, that melt flow rate number. So that is not used by the solver, but it does give you an indication of a higher viscosity material versus a lower viscosity material. So if you see something with a low melt index, let's say 5 grams per 10 minutes, you could typically say that that's going to be a higher viscosity material, so it's going to take higher pressures to fill. The higher melt index material, say we had something 10 grams per 10 minutes, we can typically say that's going to be a lower viscosity material and require lower pressures to fill. Again, this is really simplifying the flow properties of a polymer, so it is a quick and fast way to see how we could pick a higher or lower viscosity material, but it is an estimate, so keep that in mind. So as you can see, there are several factors that can affect our injection pressure. This chart basically summarizes some of the things that we covered in the previous slides, so please feel free to use this as your reference. Flow behavior. So what does a plastic molecule do in an injection mold? There are still things we're trying to figure out today in industry and the behavior of plastics, but there are some fundamental concepts that we'll cover in the next couple of slides. So there are several phases of molding. We have filling, which we're filling the cavity with polymer. Pressurization, where the part is full or almost full, so we're starting to build up pressure within the cavity, so getting into the packing phase. Then we have compensation as well, which is basically where the part's completely full. However, we continue to add material to that cavity because plastics are compressible, so we continue to add material, and what that does is helps us to offset or reduce shrinkage in our final part. So plastics are going to show something called fountain flow behavior. So the fastest flow is typically going to be in the center of the cross section. You can see from our image below how the polymer is flowing into our cavity, and then the graph on the right is showing the cross-sectional velocity. So the first material in is hitting the mold wall and freezing, so it has a velocity of 0. And as you can see, the center has the highest velocity for us. This, of course, does play a large role in not only molecular but also fiber orientation within our part. Cross-sectional flow and molecular orientation. So molecular orientation is caused by shear flow. So shear, of course, we have a laminar flow, and shear is basically being captured by the difference in velocity between the different layers. So the highest amount of shear is typically just inside the frozen layer, because our frozen layer, it of course is frozen, solidified, not moving, and then we have a still laminar flow happening just inside of that region. So we've got a layer that's basically not moving and another one moving at quite a bit higher velocity. So that difference is producing the highest orientation that we'll see, as well as the highest shear rates, as you can see in our graph below. So if we take a look at a simple 3D flow analysis and examine our cross-sectional flow in this part, we have a part with 2 ribs. The one on the left is full already. You can see the velocity is not, it's at 0 at this point, but the rib on the right is not. So we can see how the velocity vectors are pushing up towards that rib, but we can also see how between the ribs, if we look at the cross-section of this main nominal wall of this part, we can see just at the mold wall it's frozen, so we're not seeing any movement there, 0 velocity, and then below that quite a bit higher velocity. So you can see how much that cross-sectional flow can vary through the thickness of a part. If we're looking at part shrinkage, Normally, unfilled materials will shrink most in the flow direction. Unfilled materials will shrink most perpendicular to flow direction. If you see our image below here, both these parts were analyzed using the same material and the same processing conditions. What we did was we turned the fiber option off for one and left it on for the other. So in the top one, you can see we do not have the glass fibers being considered, so it's shrinking more parallel to flow. Whereas the glass fibers, it's shrinking more perpendicular to flow. This is because plastics typically, they have a tendency to try to return to a stress-free state. So when you injection mold at our injection location on the left here, we're stretching out these strings of spaghetti or these long polymer chains, and they just want to return back to their normal shape or their stress-free state. So non-filled materials, like the one on the top, they don't have the glass fibers to resist that polymer from shrinking back towards the gate. However, in the glass-filled material, those glass fibers are there. They're resisting that. However, the glass fibers offer little resistance perpendicular to flow, so they cannot help so much in that direction. So which of the following components can be found on an injection molding machine? What's the term for the feed system component highlighted below? The following image illustrates unfilled materials typically shrink more in the direction of flow than transverse to it. True or false? Which of the following variables can affect injection pressure?